Hey, pre-calc, we are continuing with 9.8. And what we have is another exercise where we have 12 marbles. We have 7 red, 5 blue, and we're just reaching in the bag and pulling out 4 marbles. So how many different sets of 4 marbles can be pulled from this bag? So what they're talking about here is just different marbles, just regardless of color. So what they're trying to say here is it doesn't matter if you picked first or you picked fourth, you're still in the same, I guess, realm of marbles. So there's 12 total. We're doing a combination of 4. I guess what I'm saying is, let's say we put numbers on these 7 red. So 1, 2, 3, 4, 5, 6, 7. And we picked out 1, 2, 3, 4. And then we picked out 2, 3, 4, 1. That's the same 4 marbles. So that's why we want this combination where the order does not matter. And don't forget to divide. So what we're looking at, if you do this by hand, 12, 11, 10, 9, and then 8. I'm going to stop there to cancel out the 8 factorial. And then we would have 4 times 3 times 2 times 1, because 4 times 3 is equal to 12. And then here, I don't know if I would really, I would probably use a calculator, to be honest with you. Or I could probably figure this out, because 11 times 9 is 99. Times 10 would be 990. So then when you cut that in half, I don't want to do the wrong answer. 495. I was going to say something silly. So how many of these contains 2 red marbles and 2 blue marbles? So think about what you could do to make sure that you have exactly 2 blue and 2 red. So again, it doesn't matter how you get the 2 of each. So what we would have is we have 7 red to choose 2, and we have 5 blue to choose 2. And here's the fundamental counting principle also happening, because we can multiply those values. I forgot where I left off, but I hope you're okay that we're doing the fundamental counting principle and a combination, that we can do 2 things at once, because we don't care how we get the red marbles and when we choose them. We just care that we do, and then we multiply those values together over 3 factorial, 2 factorial. I guess a quick way of doing this is you can cancel out some 5s there. So we're looking at 7 times 6 times 5 times 4 times 3 times 2 all over 2 times 3 times 2 times 2. So 2's we cancel, 3 times 2 will cancel with 6, and we'll say 2 goes into 4 twice. So 7 times 5 times 3 times 2. $210. There's probably a faster way of getting that answer. How many of these sets contain all red marbles? So again, sort of the same thing as up here, but we only have 7 red marbles to choose from. We just want all 4 of them to be red. So 7 factorial over the difference, 4 factorial. So I would do the problem this way, 7 times 6 times 5 to cancel out here, and 3 times 2 times 1. 7 times 5 would give me 35. And feel free to do these using a calculator as well. I'm not going to judge you too much. And you know me, I don't care too much for units either. I will when you get to calculus. And then how many sets contain all red marbles or all blue marbles? And now here's a kicker, is the word or changes operations, because we just figured out that there is 35 ways of getting all red, but then you want to add to that the 5C, we want all 4 of the blue. So we're looking at 35, and I'll let you quickly do this one. I hope that answer is kind of obvious. The more we practice things, I hope answers become a little bit more obvious for you. And I feel like I need to explain just a little bit more. So the phrase or means that one or the other can happen. So that's why we went ahead and found all of the ways to get red, which we already did in part C. Then we find all the ways we can get blue, but then we add the values together because it's one or the other. They both don't have to happen at the same time. Matter of fact, it's impossible for both of them to happen at the same time. Whereas in letter B, we multiplied because we wanted one scenario where we had 2 blue and 2 red. So I guess that word and might be a good indicator. And it's going to take practice. I don't expect you to understand this just because we did one example. And I was wrong. I thought the identity was going to be in the homework. It turns out it's right here. I'm not looking for mathematical induction here. I'm just looking for a simple way of getting from one end to the other. And I don't care if you start with the left side, that NCR is equal to n factorial over subtracting the 2 numbers factorial, the second number factorial, or if you start with the right side, where NPR stands for n factorial over n minus r factorial, all over r factorial. But it might actually make more sense if we started with the right side and work our way to the left side, because we've seen problems like this before, where when we divide by a fraction, it's the same thing as multiplying by the reciprocal. I'll change colors one more time. There's not much work to show, let me put it that way. So we have n factorial over n minus r factorial. That's the definition of permutation. But instead of dividing by r factorial, I can multiply by the reciprocal. And when you multiply a fraction, you just multiply straight across. I hope at the very least you'll get better at fractions by doing this. And that is equal to this piece, which is equal to that right side, or sorry, left side. So it's like I'm working in a circle here. I just need to show a few steps to get from one end to the other. And I don't care which way you go. Maybe you go this way. But you need something to show me that you understood that these two things are logically equivalent. And it says in the notes, but now that we've proven it, you can use this method as well. I believe that was it for that. Feel free to write down any questions. And I do realize that this homework is pretty, I think this one's the lengthy one. At least it's 4 pages before we get to 9.9 and deal with some probability. So I'll see you then on that.